Welcome, guys. Thank you for attending my talk. I'm here to present on the Shelter Protocol, which is a protocol for creating end-to-end encrypted, federated, user-friendly web applications. So my slides are going to have all sorts of entities. Some of them are real. Some of them will be AI generated. It's up to you to figure out which ones are which, just as a fun little game. Okay, so why Shelter Protocol? What is the problem that we are here to address? So Shelter Protocol emerged as out of necessity. Shelter Protocol actually emerged because we were working on a project called Group Income, and we had two design requirements for Group Income. We wanted Group Income to be decentralized, and we wanted it to be end-to-end encrypted. And of course, it needed to be user-friendly. Unfortunately, no protocol existed that satisfied all of those criteria. So we started working on what we would later name Shelter Protocol. And the reason why we wanted to do this was because we didn't want to reproduce, we didn't want to create an app and give it to users and then have to make excuses to them about why their user experience was terrible. We didn't want our users to have to deal with data breaches. We didn't want to have to deal with data breaches. And then, have to put out some blog post explaining, oh, we take your security very seriously, and, by the way, sorry to let you know all of your security was compromised. Then we didn't want to violate our users' privacy. We wanted to deliver a fantastic app to users, but we didn't want to see everything that they were doing. We wanted them to be able to use the app without us knowing. So today's web apps don't let people do that. They're full of privacy violations. Most of today's web apps have privacy settings, but none of those privacy settings are real. We didn't want to be one of those companies that gave users privacy settings and effectively be lying to our users. The way that apps are designed today, in today's industry, in Silicon Valley, results in billions of dollars worth of damages to companies, users, in terms of monetary costs as well as social costs. You might be familiar with the Experian hacks, where everybody's credit scores were leaked and all sorts of other information, their social security numbers, etc. This is a huge problem. So we don't want to do this. We want something else. So that's why we started working on Shelter Protocol. Shelter Protocol is end-to-end encrypted. And what that means is that the data, when it's stored on our servers, is stored in a way that we cannot decrypt it. There's real cryptography being used behind the scenes, and this gives users real privacy. Additionally, we didn't want to create an app that was a central point of failure. What happens if we went out of business? What happens if the internet goes down? What happens if you want to use the app that we were working on, which is called Group Income? What happens if you wanted to use Group Income and you're in North Korea and you can't access the internet? Well, federated apps can be hosted locally on your local area network. They can be hosted wherever you want. Multiple people can host them, and they can talk to each other. So we wanted a protocol that could do that. So Shelter Protocol is federated. It allows the servers to communicate with each other, and it allows anyone to run their own server. Shelter Protocol gives you not quite blockchain security, but very close to blockchain security. It gives you blockchain-like security, this kind of security that people expect with having a private key. But it does this without requiring a blockchain. We use something called contract chains. It's somewhat similar, but it's also very different. It's not a blockchain. Blockchains use a consensus mechanism, and the only way, and if you notice, public blockchains don't work without the internet, usually. You need to go to some, you need to be able to reach the consensus group. So, and we wanted to create something that could theoretically work without the internet. And we wanted finally to deliver the same user experience that people are used to today with today's web apps. We didn't want users to have to manage private keys. We didn't want users to have to see hashes. In a lot of the protocols that are somewhat similar to Shelter Protocol, users are given public key hashes and are expected to use them and to understand what those are and to work with that. We think that that's unacceptable. It's not user-friendly enough. We wanted something that was identical, pretty much, to the existing user experience that users have today with today's apps, a username and a password. So how were we able to accomplish this? Shelter Protocol is a high-level, lightweight, federated, end-to-end encrypted virtual machine. We need all of this in order to meet our two requirements of decentralization and end-to-end encryption. And you could say that actually, it's pretty simple. And this is half true. Conceptually, it is pretty simple. If you guys stick around here for the entire talk, I pretty much guarantee you that you will understand the basics of how Shelter Protocol works, and you'll be able to explain it to a friend. Here's the game plan. Here's what we're going to do. We're going to reproduce the existing user experience that everyone is already used to today, but make it secure. And we're going to do that by duplicating a list of events. This list of events describes updates to a shared state so that each client, each end user device, each iPhone, each iPad, each laptop arrives at the same exact state. And we're going to encrypt everything. We're going to encrypt this list of events. That's our plan. It's pretty simple, right? So we've been working on this for quite a long time. We've been developing Shelter Protocol simultaneously with Group Income. And it's taken many, many years for us to get to this point to speak to you about it. But we're finally here. So let's get started. At the core of Shelter Protocol, and at the core of many of the apps and protocols that you will come across at this conference and elsewhere, is the concept of a list of events. So events. Event 1, 2, and 3. The first event says we're going to do this. The second event says we're going to do that. The third event also says we're going to do something else. Here's an example event. Let's say we want to create a user, right? When a user is signing up, we want to create a user. So we need an event called create a user. So on the bottom, we see two rows. One is called updates, the other is called local state. When we create a user, the update is going to be a piece of JSON. I'm sure most of you guys are familiar here with JSON, right? Raise your hand if you're not familiar with JSON. No one raised their hand. Okay, that's great. So the local state is just going to be that. Here, our local state is now username is Bob. Next event. We want to add an email to this user. So here's our update. Here's the email, bob@example.com. And now our local state is username Bob, and we've applied the second event to that state, and we've got email bob@example.com. Now this is just a conceptual example. This isn't, the actual JSON that's being sent, but this is just to give you, it's to build the protocol in your mind, foundation level, brick by brick, until you get to the details. Finally, let's say we want to add a profile picture, same thing happens, and then here's our state. Okay, that's a start. Now, how do we store these events in a simple and safe way? We're going to use content addressing. Raise your hand if you're not familiar with content addressing. Okay, one person raised their hand. So two people. Content addressing is used in lots of places. It's used in BitTorrent, it's used in Git, it's used in IPFS, it's used in that. The basic idea is that if you want to reference some piece of content, you take that content, put it through a hash function, you get your hash, It's a one-way function. You can't go from the hash to the data, but you can get from the data to the hash. And then, actually, we're going to create a mapping back. Even though you can't derive the data from the hash, you can memorize the hash. You can remember, oh, that this hash referred to that data. That's the basic idea of content addressing. And we're going to use a key value store. So we're going to take these hashes, and we're going to put them in a key value database and map them to the data. Very, very simple. Now that actually gives us a property called data integrity. If the data is messed with, if a cosmic ray from outer space hits a hard drive bit and flips something, we're going to know because the hashes are not going to match. If the sysadmin tries to do something funny, we're going to know. So this gives us data integrity, especially when we add signatures later. So now, let's talk about what's actually in these events. We have something called the previous head. The previous head points to it's a pointer to the previous message. This is how we create this chain of events. It works exactly like Git. Git has the same thing. Every single Git commit references the previous one. And the first event is the one that references nothing, null. Okay, we have a tamper-proof chain of events. Awesome. Recap. We've got events. We say how they modify the state, sort of. Events are a content address to preserve integrity. Everything is stored in a key value database. What's next? Well, what is interpreting these messages? Better yet, what is a message? Let's start there. So here's our create a user message. This is closer. It's not exactly what a shelter protocol message looks like, but it's much, much closer. So there's a previous head, there's an op. The op means opcode. This is where we get into the virtual machine part of shelter protocol. In this case, we have an operation called action. What this means is that this type of event is an event that performs an action. And the message body says action is create a user, and message data is username Bob. Very simple. Okay, that's pretty much what I just said. So in the first event, the hash of that first event, we're going to call that the contract ID. This is how we're going to reference these contracts. This list of events that we're building, we're going to call that a contract chain. And the reason why we call it a contract, that word comes from from smart contracts. Who here is not familiar with what the word smart contract means? Raise your hand. Okay, one person. So a smart contract is a piece of code. That's all it means. It's just a computer program. And it's specifically a computer. The word contract is there because it kind of refers to a computer program that's not supposed to change. Or if it changes in very precise and specific ways that you can reference. It's kind of like a legal contract. So the first event, that's the contract ID. So the next event is tacked on to that first event. It has we fill in the previous head in this case, and so on and so forth. Here is another action. We add an email. Now, if you're familiar with object-oriented programming, then you can think of this chain of events as a record, a recording of all of the method invocations that are being made on an instance of a class. So you can think of these contract chains actually conceptually as very similar to instances of classes, a record of what happens on which object, methods are being invoked. Very, very similar. It's just a record, and that's useful because we want to recreate the same state on all of those clients across all of the devices. That's why we have a record of what's going on, so we can distribute that to all of the different clients. So what's interpreting these messages? This is where we get to the smart contract stuff that I was talking about. Let's cover that. So here is an example, some pseudocode of what a contract might look like for a user. We call this an identity contract. This is an identity contract with 3 actions on it: identity, update email, and update picture. So here we see how the event maps onto the contract. The action maps onto one of these actions. The data maps onto the data variable that is passed in to the function, the corresponding function for that action. So each action maps to a function, and that function takes 2 variables. One is the current state of the contract, and 2 is the message data that we're passing in. And very simple here, we've got one line to update the email. Or the picture or the username. In this case, we've got the username. We're setting the username. So something to keep in mind is what happens if we're creating this system and then a developer creates a contract and there's a bug in their contract. And they want to add a feature or they want to change something. Let's see what happens if we just implement this in a naive way. So here, let's start with this current contract that we have. Actually, yeah. So let's give a concrete example. You see right there where it says state.picture is equal to data.picture? That's going to be the modification that we're going to make for this example. So we're going to just comment out that line. We're going to change update picture so that the picture is no longer being set. So what happens if we first start with this contract, the one where it's uncommented, and we have a client who had this sequence of events. They created an identity with the username Bob. They updated the email to be b@e.com, and they updated the profile picture to be b.com/hi.jpg or PNG. That's going to be the state that they're going to arrive at the end. It's going to have all three fields in it, the username, the email, and the profile picture. But then let's say that now somebody wants to see their profile pictures. Now somebody wants to sync their contract to get those updates so that in the user interface they can display their profile picture. So someone comes along and gets this same exact list of events for this user Bob. But this happens after the developer has made a change to the contract, after they've commented out the code for setting the picture. So here's what's going to happen. They're going to get the exact same sequence of events, and they're going to run those events through the contract. But we're running a different version of the contract now. Well, obviously, we're going to arrive at a completely different state. That's a big problem. How do we address this? I'm sure some of you can guess. We're going to version the contracts. So we're going to content address everything, including the contracts. We're going to save a version of the contracts. We're going to content address. We're going to put that contract through a hash function, get its hash. We're going to save it in the database, and we're going to reference that version of the contract by its hash. So now we have the ability now to reference precise versions of our code. So now, if we reference the precise version of our contract code in that list of events, we make sure that these events are processed using that precise version of the code each time. So now, no matter when the developer modifies the contract, the list of events, no matter when they're synced, they're always going to produce the exact same state, deterministically. So we're good. And now, for those of you who are curious, this is what an actual contract might look like. It's very, very similar to what I showed you already. It just has some slight differences. There's the ability to validate events and things of that sort. And we're also using something called SPP instead of regular functions. Okay, you've got the basics down. Let's move on ahead. Actually, yeah, guys, let's take a little pause here to make a note of this. You actually have the basics down now. You should be able to actually describe shelter protocol to your friends now. The basic idea of how it works, we just covered that. It's that simple. That's the basic idea. So shelter protocol at the moment is comprised of 14 opcodes. And we think that these 14 opcodes are pretty much all you need to build practically any application. Here they are. We're going to go over some of them. These 14 opcodes are what give us our high-level, lightweight, end-to-end encrypted federated virtual machine. Let's start with the first one, OP contract. OP contract creates an instance of a contract. This is the first event that you send, and it's saying, I'm going to create an instance of a user. I'm going to create an instance of a group. I'm going to create an instance of something else. OP action unencrypted, we've already covered that. This is pretty much the exact same thing as the existing actions that we covered previously. Next is OP action encrypted. It's just the encrypted version of OP action unencrypted. OP key add. This adds a named public key to the contract. It specifies what they're allowed to do. It specifies whether or not they're a foreign key from another contract that must be monitored for updates. And it supports arbitrary ciphers, which means if you want to include quantum secure ciphers in here, you can. Use whatever ciphers you want. OP key add is actually part of OP contract as well. So when you create an instance of a contract, you can add your keys instantly at the beginning. OP key update either rotates an existing key. So let's say you want a user wants to change their password. You would use OP key update for this. Or updates key properties. Key properties, keys have certain properties in Shelter Protocol. Like they have permissions, which specify what actions they're allowed to perform. They also have a ring level, which specifies the precedence that the key takes over other keys. Next, we have OP key del. That just removes a key from a contract. Then we have OP key request. Every contract can request a key, a private key, from another contract. This can be useful if you want to be able to write to somebody else's contract, and you want to be able to encrypt that message with a key that somebody else has. OP key request seen is an interesting opcode. This is, remember, the server doesn't see what's going on. The server doesn't really understand what's going on in a Shelter Protocol app. And therefore, the only thing that is aware of what's going on are the end user devices. So let's say we have a group of, a few users, and one of them sends an OP key request. Let's say they want to join a group. We actually use this in Group Income for joining groups. So when a user wants to join a group, they request a key. Anyone in that group can send the key back using another opcode called OP key share. But we don't want to have everyone in that group respond with OP key share. We want to wait to limit and just say, well, anyone in the group, one person responded, okay, we don't need to send OP key share again. That's what OP key request seen is for. It just marks an OP key request as being responded to. OP key share is the actual response to an OP key request. It includes the encrypted private key. So these are the 7 essential opcodes for doing end-to-end encryption in Shelter Protocol. We have a few other opcodes, OP prop set, OP prop del. These set properties, which are just key value pairs on contracts. They can be useful for implementing additional features. And we've got OP write request, OP write request response. These request permission to be able to write to a contract. And then finally, OP atomic, which allows you to bundle multiple opcodes in a single opcode and have all of them execute at once. So federation. Federation is supported in a similar way to how Git works. With Git, you can take your chain of events and you can push and pull it from different servers, and you can do the same thing in Shelter Protocol. And this protocol has the potential to be used by something like a DHT as well. So we have a server-client approach because that's very, very simple, and that's how people are used to developing their apps, and it doesn't have all of the complicated, sometimes finicky components of DHTs. But if you wanted to use Shelter Protocol with a DHT, you probably could. And then in order to be able to recreate that experience of a username and a password, we have another sub-protocol in Shelter Protocol called the zero-knowledge password protocol. And what this does is it allows us to retrieve a salt from the server. When a user creates a password, we don't just create a private key using that password. We also use a salt, a password salt, along with their password to generate the private key. But we want to make sure that this password salt is only known to the user and to the server. We don't want anyone else to know it. So there's a zero-knowledge password protocol in Shelter Protocol which allows the user to prove to the server that they know the password without telling the server what that password is. So the server doesn't know the user's password, but the server knows that the user knows the user's password, and it can prove this in a zero-knowledge way and then send the user their password salt. And what this allows you to do is it allows you to create that username password experience on any devices. So if a user loses their device, but they remember their username and password pair, they can log in on any other device. A lot of end-to-end encryption protocols use something like QR codes and key signing and verification of like, I want to add another device to my account. I have to scan a QR code and that kind of stuff. That's how it normally works. And you can actually do that with Shelter Protocol if you want. But Shelter Protocol also allows you to reproduce the standard username and password experience. I saw you had a question. There's a Q&A period. So details we didn't have time to cover. Contract side effects. In other words, the boundary between contracts and applications. Contracts, when they're processing messages, they cannot have side effects in the processing step because that could potentially result in different state across different clients. But contract side effects can have side effects. The contract sandbox. When contracts are being processed, that processing is occurring in a sandbox so that you can run arbitrary contracts and get their state and not worry about them messing with your computer or leaking data. State snapshots. You might have a very, very long contract, but wouldn't it be cool if you could just instantly get the state of that contract without having to sync the whole thing? That's what state snapshots is about. The details of how end-to-end encryption works, we didn't really go over that. ZKP details, we didn't go over the details of the zero knowledge password protocol. We didn't go over the server API. We didn't go over usernames, and we didn't go over details in general. But if you are interested in those details, they are now, most of them, are live on shelterprotocol.net. So now we can build the same kinds of apps that we've always built while actually respecting user privacy and being honest with our users when we say that. Awesome. So let's do a quick demo. Okay, for the demo, I'm not mirroring my screen, so I'm going to be looking over here for a second. And I'm going to pull up Firefox. Okay, so let's start here. So something that's really cool about Shelter Protocol is that as you're developing your app, you don't need to worry about the cryptography that's involved until the very end when you're ready to release your app. So I'm going to run an unencrypted version of group income right now. Here are all the contracts that it's sort of saving. You have to version your contracts, so we have all of the different versions of the contracts there. And now it's spinning up a server. So now let's go ahead and I wonder if this will just, yeah, excellent. Okay, so we're using something called SPP, by the way, if you're interested. That's selector-based programming, and that allows us to log pretty much every single thing that happens in the app automatically in here. Let's go ahead and sign up a user. So U1, I've done this so many times that I can do it in my sleep at this point. So we're going to sign up a user, and we're going to create a group. We're going to call our group Turtles. We're going to set a minimum income for the amount that our group wants to distribute to people. So this is just a specific app that's using Shelter Protocol. And we're going to create a group. And the purpose of a group income is to guarantee or try to guarantee a minimum income for a group of friends or a community of people. So there we go. Voila. We just created at least three or four different contracts behind the scenes. The user didn't notice this, but they're there. And we managed to log in. So now we have a fully functioning app. We've even got like a chat room here. You could say hello. There's nobody in the group so far, but if we want, we can invite somebody to this group. So let's go ahead and invite someone to the group. So I'm going to use, I could use Firefox Developer Edition. I've got container tabs here, which are like, they're blank slates. But to really prove that I'm doing something in a completely different, environment, I'm going to use a different browser here. And I'm going to copy this invite link, and let's do this. Okay, fine. U2 ASDF.com, add a password, And then let's go ahead and join the group. So we're in the Turtles now. So now we've got, just a nice user interface. We can chat here with people. So what happens when we log out and log back in? So I'm going to go ahead and create just a private browser and log in as U1. So remember, we're not using, at this point, we're not using end-to-end encryption, so I can put whatever I want for the password and we'll log in. And then here it sees that it just logs us into the group, et cetera. In the background, what's going on is it's finding our identity contract based on our username. The username is mapped to the identity contract. It syncs our user contract. It sees that in the user contract, it says that we've joined some kind of group. It then finds the group contract, syncs that, and then gets all of the events. And then from the group contract, it sees there's a chat room contract, syncs that, sees all of these events, et cetera. And so we now have a fully functioning app, but the user has no idea all this fancy cool stuff is happening in the background. So what does it look like if we do end-to-end encryption now? So let's go ahead and, this is the wrong terminal, okay. Let's go ahead and, I will just sort of scroll here through the messages so that you can see. Here are these messages. We're calling them GI messages here, but these are shelter protocol messages. And you can see that there's a message, there's an operation, there's a manifest. The manifest is how we reference the specific contract. The operation contains whatever operation we want to have. You can see that there's somebody asking for events. You ask for events by, there's different ways you can ask for events. From one point forward, you can ask for events in a range, like given one hash and another hash, give me the events between these hashes, and you can ask for the events before a specific hash. Okay, so let's just go ahead and redo everything that we just did, but make it end-to-end encrypted. So I'm going to run, first I'm going to check out the E2E branch. Git checkout, there we go. GI persist is equal to SQLite. So the key value store, by the way, can be anything. It doesn't matter. It just needs the key value store. We're using SQLite in this case. And here we go. Almost. There we go. Okay. So I'm going to refresh this page. Okay. So we're starting from scratch. We're going to sign up a user. How am I doing on time? 33 minutes. Okay, good. U1. Hopefully U1 isn't registered already. Okay. Because I used the database, so this is actually persistent. So let's, and there, I just pressed enter. We signed up a user. So far, everything looks pretty much the same. Let's go ahead and create a group. And we'll do the same exact thing. Create a group. Welcome to Turtles. Ta-da! We've got our chat room. Now these messages, notice like everything in our app behaves the same. As I mentioned earlier, you can develop your app unencrypted. Don't worry about the cryptography. Add that at the very end. That just involves generating keys and adding them to to OP key add. And yeah, we can invite somebody, and then this invitation now. All of this this is using cryptography. We're going to invite somebody. They're going to be sharing keys with another user. We'll go into our other browser here. We'll use the invite link. Create a second user. We'll create a password, and this time actually these passwords do matter. These passwords are real. If I try to log in with the wrong password, I will not be able to log in. And there we go. So there was there was an extra. The only difference between the two apps is that there was, for a split second, an extra screen. There was a waiting to join group screen that you guys probably missed. It flashed on this on the site really briefly. That is the only difference in terms of user experience between the two versions of this app. The reason why there's a waiting to join a group screen is because you need to wait for somebody who's already in the group to send you the key to the group contract, so that you can start writing to it. And any other keys that need to be shared. If I didn't have the Firefox window open in the background, if that user wasn't logged in at that time, they would be waiting there, basically, until somebody logged into the app, and then their client would be able to share the key with them. So that's really the only difference in terms of the user experience. There's like a slight difference, but it's not that big of a deal. And we have a chat room, and we can send messages. We can, mention, whoever, hello. And then here we see that somebody mentioned us, and there's our hello message. This is all end-to-end encrypted, and I can prove to you that this is end-to-end encrypted if you don't believe me. Let me show you something here. So all Shelter Protocol apps, everything that you would normally place, almost everything that would normally happen on the back end in a MySQL database, in a PostgreSQL database, all of that stuff actually happens locally on the client. So all of these contracts are being processed locally on the client. And let me see if I can, here's a message, process message. Let's see which one of these is the message. You can see here, okay, so I'll make this a little bit bigger here. So you can see that this is all completely unreadable. See, just a bunch of gibberish. This is all ciphertext, end-to-end encryption. Okay. And in the database also, if I was to open up the database, you would see the same thing. You would see a bunch of keys, you'd see the message wrappers, and inside of the messages, it would all be encrypted. And that's what the server would see. So if somebody hacks into the server, they can't get the data. If you're interested in learning more and also about all of the different security properties of Shelter Protocol, go to shelterprotocol.net and look at the security tab. And here we cover all of the various different threat models that you might be facing and how to address and mitigate them. We've got public key cryptography being broken by quantum computers, malicious server brute forcing a password, what happens if users use weak passwords, malicious JavaScript from man-in-the-middle attacks or otherwise, malicious contracts and sandbox escape, and then compromised end-user devices. So we've tried to do our best to be as comprehensive about all of the potential ways that the security could be compromised. If you think of any other ways that we missed, please you can update this documentation yourself. So okay, I think that is about it. We've got time for questions now. So that was the demo. Questions? Yeah. Thank you. Yes.
Is this Turing complete?
Yes. So the question was, is it Turing complete? Yes, it's Turing. The halting problem. Okay. It's Turing complete in the sense that using op action unencrypted or op action encrypted, you can trigger code to run. And then that code that runs is actually running in whatever language you wrote your smart contract in. We've implemented an implementation of Shelter Protocol in JavaScript, for JavaScript, called Chelonia, and that will run JavaScript smart contracts. And in JavaScript, you can ask, how do you know that it will halt? Well, your JavaScript contract could have a while true, and it could not halt it. It could have an infinite loop inside of it, and it won't finish running in that case. Don't run those kinds of contracts. That's just the answer. Any other questions? Yes.
What would you say is like the most? Is there anything out there that's like this? That is to say, this sort of sheltered enclave that you're running, code you can't see on. What other things are like?
Okay, yeah. So the question is, what other kinds of protocols are there that are similar to Shelter Protocol? That's a great question. To the best of my knowledge, there are a few other protocols, and they all have different trade-offs and different strengths and weaknesses. So another one is here by the team at HoloChain. HoloChain also has this chain of events, but the way that HoloChain works is completely different. And as far as I know, also, I'm not sure that HoloChain focuses as much on end-to-end encryption as we do. So another protocol is Secure Scuttlebutt. So Secure Scuttlebutt, as far as I know, it might be a little bit less generic than Shelter Protocol, but it also it has better support for local peer discovery, and it's a little bit more decentralized and peer-to-peer, whereas ours is a federated model. And although you could probably take Shelter Protocol and turn it into a fully peer-to-peer thing with DHTs, we haven't done that. But ours is a client server in a federated context. And then there are some other ones. I've heard of a project called Locutus, which is an interesting one, which is somewhat similar to this one. And it's by the guy who created Freenet. And there's probably a few other. JLinks is another one. Yeah, there's a few. So any other questions?
Sorry, it's 1 o'clock, or it's 11 o'clock.
Oh, we got to wrap up? Okay. All right. Well, you can ask me afterwards. Thank you guys so much for your time. Yeah. Yeah.